Reservations in two-way slabs by means of yield lines. This video deals with slabs type 26 to 30. Those slabs have two opposite sides fixed and the other two opposite sides are simply supported. This will be case 30, which is the case when the hole is attracting the yield lines and the 30, 45, 60 rule is not valid. And it's a more general case where the hole can be situated anywhere in the slab. We take a look at case 30. It's a rectangular slab and the reservation is situated somewhere in the slab with a dimension D1 and D2 and its situation at distances D3, D4, D5 or D6. The conditions, but first, before we talk about the conditions that are there for this type of reservation, we will look at the yield lines. The negative yield lines of both where the slab is fixed is one there and also here. And we use the rule tracking the corner, tracking yield lines. So it means it's going from the intersection of two rotation axes directly to the corner of the reservation. So it's simple as that. The conditions now, it's a two-way slab, so B must be between A and 2A. Of course, the maximum dimensions, D2 must be smaller than B and D1 smaller than A. And the position, well, it's evident that A is the sum of D3, D1, and D5, and B is the sum of D6, D4, and D2. So these are the only restrictions on the case 30 hole. So now we can give some examples. You see that you have a large variety of reservations anywhere in the slab. Take care that you do not the formulas are not valid, or the method is not valid when you are too close to the edge of the slab, because otherwise now you have a yield line like this and a yield line, a negative yield line there. So they are interfering with each other, which is not very likely to happen. We will calculate the work done by the external forces in the most general case like this. So the sum of the triangles, it's always the same. It's D4 times D3 divided by 2, or you have here also D4 times D3, and you have the four corners. So these are the four corners, and it's composed of triangles, so it's 1/3 of the total surface. And it's also half, 1/2. It's the mean deflection for a rectangular, which is delta over 2. So it's 1/2 of the surface of the four orange rectangles. So it's simple as that. The work done by the internal forces now, the negative yield lines, it's m times b, and the axis of rotation is delta over d3. And we have here also b divided by b5. And now we end up with the different corners. You have in this corner, this yield line projected to this axis of rotation gives you a length of d4 and rotation angle delta over d3. So you have d4 over d3. On the other, on this side, related to this axis of rotation, you got the total length of d3 and the angle is delta over d4. So that's what you got. And we do the same for the four corners. We do exactly the same. And you arrive at this expression. We know that m is equal to q times ex over dx. And the bearing capacity is 100 times m0 divided by m. M0 is the bearing capacity of the slab without the hole. And for this case 30 type of holes, we must fulfill some conditions. We use for dimensionless parameters. So the conditions are as follows. Now we'll give an example how to use those formulas. we have here a slab 6 by 9 meters with a reservation in it situated according to those parameters. And the depth of the slab is 200 millimeters, the concrete cover 40, floor finish is 1, and mobile load 20 kilograms per square meter. What is the needed reinforcement in this slab? This is the negative yield line on both sides. We have yield lines attracting the corner, so we don't bother about this angle. And this mechanism we are going to use. The load in ultimate limit state is then 1.35 times the permanent load plus 1.5 times the mobile load gives you 38.1 kilonewton per square meter. The different parameters. And then we use the formula of the previous slides and we can calculate EX and DX. And we have as a maximum bending moment 45 times 40 times 45.42 kilonewton meter per meter. We convert this bending moment into reinforcement. We calculate the mean lever arm, which is 148 millimeters. And the needed reinforcement is 1.1 times the maximum bending moment divided by the lever arm and divided by the yield strength. And we need 862 square millimeters per meter, or at 12 diameter 12, 8 per meter is okay. It's 905. So it means top, bottom, X and Y direction. So 4 times. It's 4 times 8 diameters 12. You can also change to diameter 14. Then you adapt this lever arm. You arrive at 880, and that's diameter 14 every 175 millimeters. Now we'll give you an example of what you can do with with those formulas. You can, for instance, study what the influence is of a reservation into a slab. And this reservation is 0.2 times A, that's the D1, and D2 is also 0.2 times A, so it's a square reservation of 0.2 times A. And going from the left to the right, and you want to know what is the influence of this reservation on the total bearing capacity of the slab. So where should you put this reservation to have the least damage to the bearing capacity? This reservation means that D6, of course, this portion D6 is of course D minus A times alpha 4 plus 0.2. It's just from the geometry, and D5 is 0.4 times A. To make this movement, we see that alpha 4 goes from 0.1 times A to the this side, which is of course 0.9 times alpha minus 0.2. So that describes this type of reservation with those conditions. And alpha is of course B over A. Now we use this formula of the previous slide, put in the different variables, and we arrive at this simple equation. We calculate the work done by the internal forces, and then, like we have seen in the previous slide, you substitute the different variables, and you got a formula which is dependent on alpha and alpha 4. So alpha, it's the geometry, the general geometry, and alpha 4 is the position of this square hole in the slab. There we can put E equal to D. We calculate the bending moment, which is equal to this expression. And now we can calculate the bearing capacity, which is 100 times M0 divided by M. And M0, the bearing capacity without the hole, in the previous video, we have seen that this is this expression. Now we have Now we know that there is a restriction on alpha 4, but it's a function of alpha. This is the formulation. We know it's about this type of reservation. And you can now calculate the bearing capacity in function of alpha and alpha 4, and you can put it into a graph. On the x-axis, it's alpha, and on the y-axis is the bearing capacity. And it's in function of the size of the reservation. Now we will use this condition. It means that if alpha is 1, then alpha 4 must be between 0.1 and 0.7. If alpha is 1.5, then alpha 4 is between this. It's just filling in this condition. And if alpha is 2.0, then the condition is like this. That's why you see in this graph those vertical lines. This is the region where the formula is not valid. The other, the region where the formula is valid. Now let's look at it in a different way. We take alpha 4 as a variable, and alpha goes from 1 to 2, and then you have those three graphs. You see for alpha 1, then alpha 4 must be smaller than 0.7. You see where this function is cut off. For alpha equals 1.5, you see it's cut off at this value, and it's cut off at a value which is 1.7. It's not on this graph. From those three curves, we know now it's valid as long as we stay left of the vertical line. We can now calculate the maximum bearing loss. So that's what we are interested in. What is the maximum bearing loss in function of different parameters? So that we can choose better where to make or make not the reservation in the slab. You can minimize this function, and you've got that the minimum bearing capacity is equal to this function. It's only now a function of alpha, because it's always the middle of all those curves. And you can put this in a graph. It's almost linear, in fact. So this is alpha from 1 to 2, and this is the minimum bearing capacity. And now from this graph, you can see immediately for the type of hole that we are discussing, that when alpha is 1.4 or bigger, you have no loss in bearing capacity whatsoever. So you can make any size of reservation without losing bearing capacity. Alpha is smaller than 1.4, then you should be careful, because you can have a certain bearing loss. The alpha 4 minimum means that this is the alpha where you have the minimum bearing loss. This is, in fact, for instance, this point here. And for alpha equals 1, you will see that you have 0.4 at alpha 4 minimum. For alpha 4 minimum at 1 is 0.4. This is this point here. The bearing capacity is there 94. For the next alpha 1.5, you will see that the alpha where the bearing capacity is minimum is 0.65. And you have for alpha equals 2, the alpha 4 minimum is 0.9, and the bearing capacity is 111. So now you know that you must be careful for the reservations made in slabs with an alpha smaller than 1.4, and the critical values are given here. So you can lose only a maximum of 6% of the bearing capacity, which is that one. As an example, we take one situation, which is a square slab, alpha is 1, and in function of alpha 4. And on the x-axis is alpha 4, on the y-axis is the bearing capacity. And we see this interesting point where with alpha 4 equals to 0.236, the bearing capacity is 100%, and to visualize it, it's a reservation, and it's this situation. So in this situation, you do not touch the bearing capacity. The bearing capacity is maximum when alpha 4 is 0.4, so that when the reservation is in the middle of the slab, which is logic. So you lose 6% of the bearing capacity. From this situation to this situation, you lose 6% in bearing capacity. And on the other side, this point reflects this. So between this and this situation, between those two, you have bearing loss. And if you go outside this range, then you will not have bearing loss. And this maximum occurs when alpha 4 is 0.4, so which means in the middle of the slab. Now we've seen two different methods. We have 30, 45, 60-degree rule, and we also have attracting yield lines. Which one should you use? We can now demonstrate it by an example. You have an identical situation, identical slab with a reservation in it with the same size on the same spot. In the first example, we use the 30, 45, 60 rule to up the yield lines. So it means that this is 60 degrees and this is 30 degrees. And then the yield lines make this pattern. Of course, there's a yield line here, a negative yield line, and there also. Or we can use another system that yield lines by attraction. So it's from the corner of the reservation to the point of intersection of two rotation axes. In both cases, you have pieces of concrete slab that can rotate around an axis. So it's a mechanism, both cases. So they fulfill all conditions that there are. Sometimes, in reality, the yield lines will go to the corners of the reservations. Sometimes they will not, and you will have this type of yield line. Now let's see what the difference is. When you calculate the bearing capacity here, you have 101, and the bending moment is 1.233 times the load in ultimate limit state. And in this case, when you use attracting yield lines, the bearing capacity is 123, and the bending moment is 1.009 times the load, the applied load. So this means that using the method attracting yield lines, which is very easy to use and very quickly, gives you more capacity. So it means it's less safe. So that's a pity. And you cannot neglect it. It's almost 20% more. So using this method, attracting yield lines, you should be very careful to use that because of this. I prefer to use the 30, 45, 60 rule.